Hi there! In this video we're going to talk about partial fractions. So what is partial fractions? So to explain it a little bit, I'm going to go back to an old algebra problem. So back in algebra, if you were asked to find 3 over x plus 2 plus 1 over x minus 3, so the sum of two rational expressions, we would go after an LCD first. So we will say the LCD is the common denominator, so x plus 2 times x minus 3. And so we will multiply the first quantity by, it's missing the x minus 3, so multiply top and bottom by x minus 3. And the second quantity, 1 over x minus 3, I need the x plus 2 on the bottom, so we will multiply the bottom by x plus 2 and do top and bottom. And so what we would get is the denominator will have the LCD x plus 2 x minus 3. And in the numerator, I'm going to have 3 times x minus 3 plus 1 times x plus 2. So we continue on, and then the denominator becomes x squared minus x minus 6 once you multiply this out. In the numerator, I get 3x minus 9 plus x plus 2. And combine like terms further, the denominator stays x squared minus x minus 6. And now I have 3x plus 1x is 4x. And minus 9 plus 2 is minus 7. And we will be done. This will be our final answer. So what partial fractions then attempts to do is, with partial fractions, the partial fraction decomposition, it will give you a problem like the one we just did, and it will say 4x minus 7 over x squared minus x minus 6 equals what fractions? So where did it come from? So where did this fraction come from? Is what partial fractions is attempting to do. Where did this fraction come from? And in order to answer that question, we just did it above. So I know 4x minus 7 over x squared minus x minus 6 came from adding these two separate fractions. So I can say, well, 4x minus 7 over x squared minus x minus 6 came from adding 3 over x plus 2 plus 1 over x minus 3. And so this will be the partial fraction decomposition for these problems. So 4x minus 7 or x squared minus x minus 6, this is the partial fraction decomposition. But the question is, how do you get there without knowing, without having done it ahead of time? And so one of the things we got to look at when we look at the original problem that we're presented, so 4x minus 7 divided by this, I'm going to look for, does this factor? Can it be factored out? If we can, that means that those factors are going to be part of our partial fraction decomposition. So let's try an example, something that we don't know where it came from. Okay, so let's look at this example. Find the partial fraction decomposition for x plus 6 over x squared plus 3x. Now, one of the things we have to first look for is make sure that the degree in the numerator is smaller than the degree in the denominator. So here I have a linear x plus 6, and on the bottom I have a quadratic. So that's good. So that means it's a candidate for being able to do the partial fraction decomposition. The other thing that we have to look for is to make sure that denominator factors. So does this denominator factor? So that's the denominator factor. Yes, in this case, notice that we have two terms. So look for a common factor. In this case is x. So x times x plus 3. So what this means then is that I can break this up, just as we did before, into the fractions from the two factors. So one with an x, and the other one is going to be an x plus 3. Now, going back to the one that we did before, notice that we had the factors here for this quadratic were also linear, x plus 2 and x minus 3. And notice that above we had constants. Now this came from doing the original problem up here, but notice that when I have a linear factor, I have a constant term above. Linear factor, constant term above. So here I have linear factor, so I should have a constant term above. Linear factor, I should have a constant term above. So we're going to call them A and B for the constant. I don't want to have another linear factor here like x, because then notice that I would be able to cancel the x's. If I'm able to cancel the x's, that means that my original problem had the same degree, where I was able to cancel something there, but I wasn't, right? Notice that here the degree is 1, here the degree is 2, and nothing cancels. So I shouldn't be able to cancel anything in here. So now, how do I solve for the a and the b? And now we're going to treat it like an equation. So the goal is to solve for a and b. And I will show you 2 ways to do it. So we'll start with the first one. So I'm going to have x squared plus x over x squared plus 3x equals a over x plus b over x plus 3. And our goal is to solve for a and b. So we want to get rid of the denominators. So multiply both sides by the LCD. So my LCD is x times x plus 3. So multiply both sides by LCD. Which multiplying both sides means multiplying really each term by the LCD. So x times x plus 3, multiply this by x times x plus 3, and this by x times x plus 3. So it's essentially when you multiply both sides, here I'm just distributing in already. And so notice that here the whole denominator cancels because this was our LCD. Here the x's cancel, and here the x plus 3's cancel. So we're left with the numerator on the left, and here the a times x plus 3 plus b times x. And so this part is the same for both methods, and I'm going to show you the method of combining coefficients. So what this means, I'm going to have x plus 6. So notice that the coefficient on the x here is a 1 equals, and then when I multiply the ax here, so I'm going to have ax plus 3a plus bx. So I'm going to gather the coefficients that are the same. So ax plus bx. So I have ax plus bx plus 3a, and we're going to factor that x out. So I'm going to have a plus b, and I'm going to have the x. Even though I'm factoring the x, I'm going to put it on the right side so that the a plus b is the coefficient, plus 3a. So combining coefficients or gathering coefficients, what it means is that now an equals is a very powerful thing. So I have this left side is equal to the right side. Notice I have an x term, I have an x term, and I have a constant term, I have a constant term. So what this means is that the coefficients have to be the same. So maybe I should call it equating coefficients instead of combining coefficients. So let me say equating coefficients, because I'm really saying that these coefficients must be equal. The coefficients of the x terms have to be the same, and then the constant terms have to be the same. So what I get is that then 1, the coefficient of the x has to equal the coefficient of the x on the right, is a plus b. And the constant terms is 6 on the left, so 6 has to equal 3a. And now this one helps me solve for a. Divide both sides by 3, so a is 2. Now that I know a is 2, I can plug it in here and solve for b. So I'm going to have 1 equals a, which is 2, plus b. And now I can solve for b. Subtract both sides, 2 from both sides, so you get b is equal to negative 1. And let's go back to our partial fraction. Our original problem said x squared plus 6 over x squared plus 3x is equal to a over x plus b over x plus 3. So let's go back. What we just found the values of a and b, so we can say therefore x plus 6 divided by x squared plus 3x came from 2 over x plus negative 1 over x plus 3. So we can really say 2 over x minus 1 over x plus 3. And so this will be the partial fraction decomposition for this problem. Let's try another example. So before we try the second example, I said I was going to show you two ways. So this one was equating coefficients. So the other method is what I call the cheap and easy way. So back to where we had it after we had gotten rid of the excuse me, the denominators. So I had at one point I had x plus 6 equals, I had a times x plus 3 plus bx. So just to bring you back to where we were looking at that. So this at the start, the process is the same. So you factor the denominator, then you write the partial fractions based on those factors. We clear the denominators by multiplying by the LCD. And once we are at that step where I've cleared the denominators, so this is where we're going to either equating coefficients or finding the zeros. So this method is gonna be finding zeros. So once I'm here, I have a times x plus 3 plus bx. So what finding zeros means is for each of the factors, we're going to ask ourselves what makes this 0. This is equal to 0 when x is equal to minus 3. And this is equal to 0 when x is equal to 0. So we're going to choose those values. So let x equals minus 3. So when x is minus 3, we'll plug it into the entire thing. So I'm going to have, so plug it into the left side as well. So I'm going to have negative 3 plus 6 equals a times negative 3 plus 3. And the reason that I chose minus 3 is because then it's going to help me get rid of that a. So it's going to go to 0. And I'm going to be left with b times negative 3. And so what are we left with? So I'm going to have negative 3 plus 6 is 3 equals negative 3b. Divide both sides by negative 3, and notice that you get that b is equal to negative 1. So it's the same answer that we got before. Now let x be 0. So when x is 0, again, plug it into the whole thing. So plug it into the left side, so 0 plus 6 equals a times 0 plus 3 plus b times 0. And so I get 6 is equal to 3a. Divide both sides by 3, and we get 2 is equal to a. So it's the same answer, we just got there a lot quicker. So finding zeros tends to be, I call it the cheap and easy way, because things go a lot faster than when you're having to equate coefficients, because then here you have to multiply stuff out, then gather like terms and factor out the common variable, so either x or x squared, as we'll see in future examples. So let's set up another problem. So say you want to find the partial fraction decomposition for 2x plus 1 over x squared plus x minus 2. So what is the first thing you're going to ask yourself? The degrees. So look at the degrees. Is the degree in the numerator smaller than the degree in the denominator? Yes. So that's a candidate for partial fractions. We have to have a degree smaller in the numerator. So it's a linear and a quadratic in the bottom. We're good. The next thing to be able to do partial fraction decomposition is, does the denominator factor? So can you factor this? If you can, then we're going to be able to break it up into fractions that, where did it come from? What fractions did it come from? So that's a factor. Two numbers are multiplied to -2 and add up to +1. So that will be x plus 2 and x minus 1. So yes, it does factor. So I can go ahead and write my partial fraction decomposition. So I can say 2x plus 1 over x squared plus x minus 2 is going to equal to, it has two factors, so I'm going to have two fractions. So x plus 2 and x minus 1. And by the way, if you end up writing it as the x minus 1 first and then x plus 2 second, that's fine, right? The constants that we get on the numerator they're gonna match up. So if I write it this way, whatever answer I get that goes on top of x minus 1, that's what you're gonna get going on top of your x minus 1. So it doesn't really matter which factor you write first. Okay, so what goes above? This is a linear term, so I should have a constant term above. So linear term, constant term above. And then you will go through the process, clearing the denominators and then finding a and b's again, either by the equating coefficients method or by finding zeros method. So let's set up a few more just to see what they will look like. And I'll record a second video actually solving them. So we're just gonna set up the partial fraction decomposition. So we won't solve for the coefficients. Set up the partial fraction decomposition. Okay, so let's try these two. So again, with partial fraction decomposition, first thing is check that your numerator has a smaller degree than the denominator. The degree here is 1 and the numerator, the degree in the denominator is 3, so we're good. The next thing is, does this factor? So can you factor it? And yeah, notice I have two terms, so I can factor the x squared. So I'm left with x minus 5. Now this one's a little bit trickier because now I have a square there, and this is a repeated factor. If you really factor it, this is x times x minus 5. Right, so x is still a factor, x squared is a factor, and x minus 5 is a factor. So x squared, and x minus 5 are factors. So what that means then is that when I write the partial fraction decomposition for this, I'm going to have an x, so a constant on the top, plus x squared, because x squared is also a factor. But this is a repeated linear factor, so I'm still going to have a constant term above. So this is a repeated linear factor. So I squared, and then my other term, x minus 5. So I'm going to have a c there. So those will be my partial fraction. Now I end up, if you're wondering, well, why do I have the x there? The factors are really just x squared and x minus 5. But it's really, think about what can be divided. What can you divide into x cubed minus 5x squared? You can, and x goes into it, but x squared also goes into it. So we need to have that x. So because we're trying to think, where did this fraction come from? How were we able to get this common denominator of x squared times x minus 5? I can't just say that it didn't have the x term, that it was just these two. Because what if it did? And if it turns out that we don't, what we'll find is that the a is 0. Now for this one factor, I can already see that the degree in the numerator is 2 and the degree in the denominator is 3. So we're good on degrees. For the factoring, I can take out an x, and I have x squared plus 4. Now this is a quadratic that does not factor. So this is what's called an irreducible quadratic. So it's not a repeated linear factor like that x squared was. So what this is going to look like then is a over x, my linear factor, plus, now I have x squared plus 4, which I cannot factor, and it's not a repeated linear factor. So now I need to have a linear term above. So usually we think of a linear equation as y equals mx plus b. This is the most general linear form. So in this case, we're going to say, just to keep in the theme of the capital letters, I'm going to say bx plus c. So I have a quadratic on the bottom, I need to have a linear on top. Okay, so just to kind of illustrate this a little bit more, so if I have something like x minus 1 over x squared times x squared plus 9 squared, for example, notice that I have repeated factors, so this will be a over x plus b over x squared, right, for this x squared, because then that means that all the possible factors of these are x squared, x squared plus 9, and x squared plus 9 squared. So sometimes listing out all the possible factors is a little bit easier to see it. So then I need to include all of them. So then I'm going to have plus the x squared plus 9, which this is an irreducible quadratic, so I need a cx plus d. I need a linear up top. And this is the repeated factor of that. So where am I? A, B, C, D, EX plus F. And sometimes when you start getting too many letters, we kind of go by saying A1, A2, A3, A4, A5, A6. Okay, so in the next video, I'm going to do some examples of how do you then find the values of the constants, the A, B, and the C.